Time's 11 o'clock, so let's get started here. So project number 4 is due now. If for some reason you were unable to turn it in to me, please come talk to me after class. Test number 2 is next Tuesday, so we will spend part of our next class reviewing for the exam. Are there any questions before we get going here? Okay. We left off in the notes about page 926. We'll finish up chapter 9 today and start chapter 10. Note also that there will be one more project this semester, but it will be shorter than previous projects. It's just I want to give you some experience with the chapter 10 stuff, so that's why I do have one more project left to go. Oops. Okay, so last time we left off talking about forward selection, and this corresponds to step 2 of the 4-step model building process, where what we're trying to do is remove particular predictor variables that may not be helpful in predicting the response variables. So remove them from consideration, so that we can move on to step 3, which allows you to refine the model. So with forward selection, what we basically did was we started with a model that had no variables in it at all, no predictor variables, and then we, one at a time, added predictor variables in the model as long as they were found to be important, given what was in the model in the past. Well, now we're going to talk about what's called backward elimination, which goes in the opposite direction. We're going to start with a model that has, let's say, all our predictor variables in it, and then one by one remove predictive variables until we get to a point where all the predictive variables that are in the model are truly appear to be important. Okay? So here's how it goes. Start with all the predictive variables in a model, and then estimate that model and remove the variable that is least important. Then starting with this new model that you just found, that has one less variable in it, look to see if there's any variables that are non-important. Remove one of them. And then you keep on going to a point when you cannot remove any more variables because all the variables remaining are important. Well, how do you decide what's an important predictor variable? Well, the same ways that we did with forward selection. We could use, for example, hypothesis tests. So let's consider a situation where we have 3 predictor variables of interest, x1, x2, and x3. And what we can do is perform a t-test. Let's assume that these are continuous predictor variables, where we estimate the model that has all 3 variables in it, and then we do a test corresponding to x1 given x2 and x3 are in the model. And suppose that p-value is 0.01. Then we go to x2, given an x1 and x3 in the model, perform a t-test. Suppose you get a p-value of 0.05. And then lastly, suppose we go to x3, with x1 and x2 in the model, and suppose you get a p-value of 0.50. So given this information, which variable do you think we should remove first from consideration? What one?
X3.
X3. So we would remove then X3 from the model because we have a don't reject HO for it, meaning that there's not sufficient evidence that this variable is important. We'll talk about the ramifications of removing that in a little bit. So then we go to the next step, where we look at a model that has x1 and x2 in it, and again we set up some t-tests, and we look at x1 given that x2 is in the model. We look at x2 given that x1 is in the model, and suppose we get p-values such as this. Which variable is the least important according to a t-test criteria? x2. Should we remove it? No. Because it does have a kind of a small p-value. So then backward elimination stops. It says, okay, we're going to work with X1, the model with X1 and X2, and move on to step 3 of the model building process, which looks at refining this model, such as looking at interaction terms, looking at quadratic terms, or other transformations of your predictor variables. So that's how this works. Now, what we could also do alternatively is use the AIC. Remember with the AIC, the smaller the AIC, the better the model. So consider a situation where the model with X1, X2, and X3 in it has an AIC of, let's just say, -2. And when I look at a model that has only X1 and X2 in it, okay, suppose now that my AIC becomes, let's see, -1. Suppose we consider a model that has X1 and X3 only in it. Suppose my AIC is now, let's say, -1.5. And let's look at a model with X1 and X2 only in it. Suppose my AIC is now -3. Given this information, which is the best model? The model that has only X1 and X2 in it. So, you know, what this says is, okay, let's remove X3. Then I go now to a situation where I look at a model that has X1, X2 in it only. It has a AIC of -3. And suppose, now those aren't erasing. Suppose I look at a model with only X2 in it and a model with only X1 in it. And I get an AIC of, let's say, -2.5 and -2.75. Should I remove any more variables? No, because my AIC is actually going up. So again, the smaller the AIC, the better, so that I stop. I conclude that my model right now has X1 and X2 in it. Move on to step 3 of the model building process. So that's how it works. Any questions? Okay, let's jump ahead to an actual example with the MBA GAR data set. This is on page 930 of the notes. Let me actually go over here to 10. So if you remember from last time, there's a function called step in R that does forward selection for you using AIC. But we can also use this function to do backward elimination as well. To begin here, we need to estimate a model that has all of our predictor variables in it. And then we use the function step again, where notice we pass into it for its first argument the results from the model that has all the variables in it. Say direction equal backwards, or backward. Scope, that corresponds to, well, what's my lowest model that I could have, which would be no predictor variables. And what's the highest model that I could have? That would be the model with all the predictor variables. And then k equal 2 corresponds to, I want the AIC. If you remember, with AIC, there's that penalty, that 2 times p. That 2 corresponds to the coefficient on p. So I put the results into step.back and just look at a summary of the results using step.back $ ANOVA. This is what I get. Hold on a second. It's odd. Well, my mouse isn't working. I'll have to use the touchpad. Bad timing for the battery to go out. Anyway, so we have a the model with all the variables in it has a AIC of -479.89. And then I look to see, well, what happens if I were to remove, notice the negative in front of the FTP, or the minus sign. What happens if I remove FTP and look at a model with all the remaining 4 variables in it? my AIC goes down to negative 41, so that says that, yeah, it looks like the model improves when you remove FTP. If I remove age, my AIC actually goes up. So you don't want to remove age, and you don't want to remove any of the other variables. So this says, let's remove FTP. So now, notice how my AIC here is negative 41.84, for the model has 4 variables in it. And notice if I were to remove any other variables, my AIC goes up, so therefore I stop the backward elimination process. Let's see if I have an extra battery here. Hold on. Any questions? Oh, yes. Always come prepared to class. Okay, well, we could also approach this using the hypothesis test. So let's just briefly look at that. This is located on page 934. If you remember, I constructed a function called test.var, which allows you to do hypothesis tests. So in this particular case, if I start with a model that has all the variables in it, I look, well, what happens if MPG is removed? That means I need to estimate 2 models. The HO model does not have MPG in it. The HA model does have MPG in it. What test.var then does, it puts a p-value into MPG for this particular test. I can do this for the other 4 variables as well, and I get to a point right here. So, which variable has the largest p-value? FTP, 0.82, which says since that's large, let's go ahead, remove FTP from consideration. So I remove FTP from consideration, and now again I proceed in the same manner, where I look at the models that has 4 variables in it to a model that has 3 variables in it. So with MPG, notice the HO model does not have MPG, the HA model does. You see the 4 variables. Put the p-values into those corresponding objects, and here we go. Notice none of the p-values are exceptionally large, so I stop. So notice we get to the same place as we did with AIC. Now, how do you know, with respect to these hypothesis tests, what's a large p-value, what's a small p-value? Well, a recommended level of significance is 0.3. Notice that this is larger than usual. It's because it's trying to guard against removing variables that maybe later on will indeed appear important. So that's why, generally speaking, a larger alpha than usual is used. So that's backward elimination. One could also do what's called stepwise forward selection, which is a combination of forward and backward. Simply, you go forward, and then you do the forward selection to find the most important variable. Then you do backward elimination. Then you go forward again, and you do backward elimination. You keep on alternating between the two until you get to a point where no variables can be added to the model and no variables can be removed from the model. So simply put, here are the following steps. Start with a model that has no predictor variables in it. Then try to find the most important predictor variable to add to the model. So simply, you can fit simple linear regression models for every single predictor variable. Find ones that maybe have low t-test p-values. The one that has the smallest p-value, add that to your model of interest first. Then go to all 2 predictor variable models. Look to see if you can add a second predictor variable. And then, once you add a second predictor variable, that's when you do a backward elimination step. to see if anything can be removed. If nothing can be removed, go to the forward selection again, one step, then go backward, and keep on going back and forth. What's that?
Isn't it kind of redundant?
No.
Based on the way that we did.
Well, it's not redundant in the sense that once you add, let's say that you added x1 first, and then you add x2. Well, now that you've added x2, maybe, given that x2 is in the model, maybe x1 is no longer important. So that's where it would be removed. So that's the benefit from doing that. If we jump ahead in the notes to about on page 931, you can see how to do this with using the AIC. Simply, I estimate a model that has no predictor variables in it to give it a starting point. Then I use the function step again. The main difference from what we've seen before is now I have direction equal both. And just to illustrate something here, I put trace equals 0. What that tells R is I don't want to see every single step given out as what you see on, for example, page 929. And so in the end, I just use step.4 $ANOVA, and that gives me a summary of what has happened. And in this particular case, it only added variables and never ended up removing any variable. It ends up with the exact same model that we had before. Again, this is not always going to happen in practice, but that's what happened for this particular data set. Okay. For last time, let's go back to page 928 now. So as I say here, these model selection procedures do not always end up with the same model. And especially if you have personal knowledge about a particular set of data. Maybe you're collecting the data for your own research. This is especially true for non-statisticians who are here. You will have maybe some prior knowledge about a particular problem. And if you, let's say, in the context of our MBA example, if you know that, let's say, MPG squared should be important in the end, maybe based upon your knowledge of the problem, but let's say MPGs actually was removed during this model building process here, or this forward selection, let's say, or backward elimination. Well, what's going to happen then is in step 3 of the model building process, you're not going to have an opportunity to look at MPG squared now, because MPG was actually removed from consideration. So this is where it's okay that you could still consider a model that has MPG and then move on to step number 3. So even though one of these selection procedures said remove MPG, it's okay to leave it in based upon your prior knowledge. In step 3, though, you will have an opportunity to say, okay, even MPG squared is not important, so let's just remove MPG and MPG squared. Okay, so you still will have an opportunity to do this. Now, there's also some other problems with these model selection or predictor variable selection approaches. For example, when we're doing hypothesis tests here, we're doing tests of this form. Is a beta equal to 0 or not? So if you end up concluding that don't reject HO, does that mean that beta is equal to 0? Well, let's think about it in terms of backward elimination. For example, with the FTP variable, I had a p-value of 0.82, which said don't reject HO. So according to that selection criteria, we would remove FTP from consideration. But does that mean its corresponding beta is equal to 0? If I say don't reject HO? The answer is no, because you can never say that HO is true when you do hypothesis testing. So you can see then here a defect in these predictor variable selection procedures is that by removing FTP from the model, we are essentially saying, yeah, beta is equal to 0 for it. But that's a problem. They might be saying, well, why do we do this? Well, you need to somehow be able to narrow down your variables. And this is just one way to do it. But given what I had just mentioned here with the hypothesis testing situation here, this is one reason why some people prefer the AIC. Because the lower the AIC, the better the model. And you're not necessarily making those kinds of conclusions that you would with hypothesis testing. But again, just as a reminder, this is where, again, your knowledge of a particular problem can be very helpful. That if you knew that, indeed, FTP should be important, no, it doesn't hurt to still leave it in the model. You can always remove it later on. Okay? Also, another potential problem here is that with this backward elimination, forward selection, when we're doing it with hypothesis testing, how many hypothesis tests are we doing here? Are we doing 1, 2? Well, we're doing quite a few. What's the problem with doing a lot of hypothesis tests?
Your type 1 error rate.
Exactly, your type 1 error rate could potentially, your overall type 1 error rate could potentially build up. So that's another problem. And another reason why some people now, especially now, prefer the AIC. What's your question?
Why does it matter how many problems? Like, I get the reason, but...
To relate this to something that you and many other students have had before, is it goes back to like Stat 802. When you're doing multiple comparisons of means, either when you're doing confidence intervals or hypothesis tests, you're doing a lot. And if every single time you have a chance of error of 5%, that potential error builds up. And so that's why there are many procedures that are used to control the overall family-wise error rate.
But like if you didn't find anything for like 3 hypotheses, can't you just say, never mind, and then the error go away? Or like,
Well, still, by doing any kind of hypothesis test, no. The problem is you never know when you actually are committing an error. And so anytime you do a hypothesis test, you're opening up the possibility of making an error. And because of that, your chances of error are just going to increase overall the more hypothesis tests you do.
if you like don't include them in the end,
What do you mean by you don't include them in the end? You don't tell anybody that you did those hypothesis tests?
Yeah.
Well,
And does it go away? Like, I just never understood that.
no, it doesn't, because you're still doing it, so there's still a chance for error. We can talk more about it after class if you want. Was there?
I think I kind of like the same. It feels like when you say like you do more, it feels like it's changing the data somehow to make it less good. But I think like for each individual test, the p-value is still the same. It's just overall you have to include them all. So it's like if you do more tests, it's not going to change the data for that one particular comparison. It's just overall. It's just I think people are kind of, it makes them think that the data is changing the more tests you do or something like
Well, the data is not changing. Is your understanding of the data could change based upon doing lots and lots and lots of hypothesis tests. And we want to have a correct interpretation of the data. And one tool that we use is hypothesis test, but we know that we have a chance of error. So I don't know if that corresponds to what you were saying or not. So are there any other comments? Okay, let's move on then. Let's see, I think that takes us to the end of the chapter. So, read section 9.5. They have, the authors have some comments similar to what I had about these model selection procedures. Section 9.6 talks about model validation. As I said at the beginning of this chapter, this is step 4 of the model building process. oddly, our authors of our book decided to put it in Chapter 9, when in Chapter 10 we do Step 3 of the model building process. So it kind of makes sense. Well, why don't you just do Section 9.6 then after you do Chapter 10, which is Step 3. So that's what we're going to do. Section 9.6 is not on your exam then, obviously. But otherwise, it's all the rest of the stuff that's from Chapter 9. And this actually then concludes then the material for test number 2. Okay, so Chapter 10 now. So this is now, again, Step 3 of the model building process, which says, okay, you've narrowed down your possible set of variables that you wanted to include in a regression model. Now, let's look at if any changes need to be made. You know, do I need an interaction term? Do I need a quadratic term? Do I have maybe some outliers? Do I have problems with non-constant error variance? So a lot of the stuff here that we're going to talk about was kind of talked about in Chapter 3 and Chapter 6. But now we're going to go into more detail and also look at some better measures than what we could, for example, back in Chapter 3 due to the material that we had covered so far. And so Section 10.1 looks at a topic that we've addressed before, and that is once we have a particular predictor variable in our model, we need to figure out, well, what is the correct form of that predictor variable? Do I need, for example, a quadratic term? And one way to then make that determination is with what are called added variable plots. Some people also call these partial regression plots as well. So just as a review, because this builds upon some other stuff that we've done, if you remember in Chapter 7, we talked about this thing called extra sum of squares. So for example, SSR parentheses x2 given x1 represents this. How has my SSE decreased when I add x2 to my model given that x1 was already in the model? So if x2 is important, you expect SSE to decrease a lot. If it's not important, well then my SSE is not going to decrease much. In Chapter 3, we also talked about a plot of the residual versus your predictor variable. And we said something like this. If I have, here's my residual, here's my predictor variable. If I have just a simple random scattering of points here, then that says that x is in the correct form for our model. If, however, I have some kind of, let's say, maybe a linear trend amongst the points or a quadratic trend, this just suggests some kind of transformation is actually needed. Now, the problem, though, with doing a plot like this, even though it's commonly done, is it doesn't account for the fact that there are other predictor variables that may already be in your model. So what would be nice is this. If we come up with a plot that says, okay, consider a situation where you have x1, x2, and x3. It would be nice to have a plot where I can say, given x2 and x3 is in the model, could I look at a plot, let's say the residuals versus now x1 that's modified for the fact that I have x2 and x3 in the model. And look for, well, what's the correct form that x1 should be in the model? And that's what we're going to talk about here. In essence, these plots that we're going to talk about are kind of like a graphical form of a t-test. Remember, a t-test basically says, given x2 and x3 is in the model, let's test the significance of x1. So again, these kinds of plots are going to be called added variable plots. Let's consider a simple situation where we have just x1 and x2. And here's how you construct one of these added variable plots. Let's say I'm interested in x1. That's what variable I'm interested in. I want to determine what's the correct form for x1 in the model. First, find a sample regression model using y as the response and only x2 as the predictor variable. So you can say maybe my predicted value of y which we normally call y hat, we could, to emphasize that only x2 is being used, y hat parentheses x2. So given x2 is in my model, let's predict y. Then we could find the corresponding residual as well. Again, a little modification to our notation. E, then my model is y, given x2 is in my model. And as you would expect, you take your y minus this corresponding y hat. So essentially what we've done here is, what we have then left over in these residuals is the effect, or we have basically y after we have removed the effect of x2 has on it. After we remove the association x2 has with y, that's what's remaining in this residual, because that's a residual. So what's left over. You know, if x2 and y were perfectly correlated, with a positive correlation, of course, there's nothing left in E, or there's nothing left in Y, so the E's would be 0. Generally speaking, that's not going to happen. So, you know, we have these residuals here that measure Y with the effect of x2 removed. Then, now use another, or estimate another sample regression model where x1 is the response variable. Not a predictor variable, but a response variable. And we're going to use only x2 to predict it. So you can say that maybe our model looks something like this, where we have x hat 1 to represent the predicted variable of x1, given x2 is being used to predict it. Then a residual for this model would be E parentheses x1 given x2. So we just take x1 minus its corresponding predicted value. So now, similar to what we had in step 1 there, what we've done is now remove the effect that x2 has on x1. Or again, another way to think about it is you remove the association that x2 has with x1. And that's what's left over in this residual. So essentially, we have two different residuals. Both have removed the effect of x2. And so now you would think, well, if x1 had an association with y, given that x2 was already being considered, you would expect to see that association represented in a plot of these two residuals. And so what we do is we plot these two residuals, and this is what's called our added variable plot. If we had more variables under consideration, well, then we just make the expected adjustments to where our residuals would be. So let's take a look at some plots. So let's say that after we account for x2, suppose that x1 is really not helpful to predict x1. Then this is what we would expect one of these added variables plots to look like, a random scattering of points. And again, just think about what this means whenever you see a random scattering of points in a regular scatter plot. What happens with the x-axis is not affecting what's happening with the y-axis, essentially. But instead, let's say that we had this plot, where we see this linear trend here, roughly speaking. And what this says is that after you remove x2, there is still something left over in y that's linearly associated with x1. So what this plot's saying is, yes, x1 should be in your model even if x2 is already there and should be in a linear form. If instead we had a plot that looked like this, maybe kind of a quadratic trend, that says now that there's actually a quadratic association between x1 and y, given that we've accounted for the effects of x2. So again, here you can see that what this plot's representing is basically what one of these t-tests is giving us. You know, t-test allows you to say, given a particular variables in your model or other variables in your model, what's the effect that this particular variable has on the response? We have a graphical representation of that. The advantage of doing this plot rather than only relying on t-tests is that this gives us a measure of the type of association, linear, quadratic, or maybe something else, where t-tests would not necessarily give you that unless you had specifically, let's say, a quadratic term in your model. Okay, so these are added variable plots.
This assumes that you knew correctly what the form of Residual was.
Yeah, and that's also a problem because what this is saying is that you have the other variables correct. Yeah.
You have
But there's nothing.
variables, there is no end to it. Then.
Well, nothing's going to be perfect, unfortunately. But I think this is still a step in the right direction to try to figure out what the correct form of a predictor variable is. Just be careful. The interpretation here with these plots is somewhat different from the plots of the residual versus the predictor variable. In particular, this random scattering plot, random scattering of points in this plot. When we would see something like this where we just plot the regular old residual versus the regular old x, we would say x is correctly specified in the model. That does not mean the same thing here. Instead, it says that x shouldn't be in the model, basically. Let's see what else. I'll let you look at the rest on your own. Note that in Fox and Weisberg's book, they talk about a component plus residual plot, which has the same purpose as what we have here. But we will not talk about it in this class. You're not responsible for it. So let's go on to the MBA GUARD data set once more. The function that does these plots is called AV plots. It's in the CAR package. Please remember, or please note that there is a small change to the name of the function itself. Fox and Weisberg, again, the authors of the CAR package, in their first edition of their book, which only had Fox as the author, called this AV dot plots. Then when he brought on a second author, he decided to, I guess, do some changes to the function in his package, and so he removed a lot of dots from the names of the function names. So with this particular case, the model I'm going to consider has all of our predictor variables in it except for FTP, because we found in Chapter 9, which was Step 2 of the model building process, it didn't look like FTP was going to be helpful. So we used the model that has 4 variables in it. We put the results into mod.fit from using the LM function. We call the CAR package, and then we simply say AV plots mod.fit, and this is what we get. What I have there in blue is just basically in our notation what's the y-axis, what the x-axis is for one of the plots to help you out. So in the what I would say the 1-1 plot, row 1, column 1 plot, what we have here is the residual for using ppm as a predictor variable and height, field goal percentage, and age as, ppm as the response variable, height, field goal percentage, and age as the predictor variables. And then on the x-axis we have MPG as the response, height, field goal percentage, and age as the predictor variables. And again, what we're looking for here in this plot is there any particular kinds of trends. And by default, the function will put a simple linear regression line on it. And notice we only have one, basically, in this case, we have one thing on the x-axis, one thing on the y-axis. That's why simple linear regression model can be fit. And we see kind of an upward trend there. It's not strong, but what this is saying is that, yeah, there might be a linear relationship between MPG and ppm given the other 3 variables are in the model already. In the notes I mentioned that, well, maybe there's a slight quadratic trend. I think this is stretching it. I might revise my notes next time, but I think that's what I was kind of seeing there. So take a look at the other plots. Let's look at the plot for height. Again, maybe a linear trend, and again, maybe this is stretching things a little bit here, but maybe we can see a little bit of quadratic going up. Field goal percentage, maybe a linear trend, and also age, and maybe linear trend if anything. But overall here, what we're getting is that these variables may be correctly specified in the model in terms of their form, but we might want to look at some transformations just to see what would happen. How can we look at those transformations? Do some hypothesis tests. Look at AIC with these additional transform variables in the model. Okay, that's section 10.1. Are there any questions? So now, once we've done this, then, we want to look to see, do I have any outliers? And we're going to look at two different ways to look for outliers. So far, we've talked about the semi-studentized residuals. That was done primarily as a way to get you thinking about the idea of outliers. There are better measures than semi-studentized residuals, and that's what we're going to look about here today. And after today, we won't look at semi-studentized residuals anymore. We'll just look at these other measures. So here's, I think, a good plot to help demonstrate what we're going to be doing. Consider a situation where you have a response variable y, predictor variable x. Now, if points 1, 2, and 3 were not in your data set, you would expect a regression model to go through the middle of the points like that, right? And in fact, maybe I'll just, for demonstration purposes, extend this up to there, okay? Now, what would happen if observation 1 was added to the data set? What would happen to this line, do you think? It would shift a little bit towards the line. But look where this point is relative to all the other points. It's kind of in the middle of the axis. Yes, it is an outlier. We can see it compared to the rest. But this is a case where it's not necessarily a detrimental outlier. Because now what's going to happen to your model is this. It's going to shift, and I think this is actually too dramatic. Let me try drawing this again. It's going to shift. This is meant to be a straight line. It's going to shift just a little bit up. But overall, is this really going to change your interpretation of the relationship between x and y? No. Look at the slope. The slope is pretty much the same. Remember how we focus on that slope to try to understand the relationship between x and y. Oops. Close this. Okay. Now let's suppose that observation 1's not in the model. I'm sorry, not in the data set. Suppose we have observation number 2, though, in the data set. What do you think is going to happen? And obviously we can see it's an outlier, meaning it's far distance from all the other points. It's an outlier with respect to the axis because it's far from the rest of the axis. It's also an outlier with respect to the y's because it's quite different from all the other y values. What do you think is going to happen to the model when I put observation 2 in the data set? Not going to really change much because it's just continuing the same trend. So again, this is a case where, yes, we do have an outlier, but big deal. It's not really changing anything. Okay? Now, what would happen if observations 1 and 2 are not in the data set, but now observation 3 is in the data set? Notice that this is an outlier with respect to the x's, because it has quite a different x than the rest, but not with respect to the y's. What do you think is going to happen in this particular case to the model? Is the red line going to stay, or is the model going to stay the same? Is it going to change? How's it going to change? The slope of the line is going to change. In fact, what happens is that the observation 3 will pull the line towards it. It will exert influence on your model. Maybe not as dramatically as I drew there, but it will exert substantial influence. Observation 3 is a case of an outlier which we are very concerned about. Because notice what happens to the slope. The slope changes. And again, we focus on the slope to understand the relationship between x and y. So thus, your understanding of the relationship there will change if observation 3 was in your data set. We want to find these particular cases and try to take some what are called remedial actions, if needed, to maybe, let's say, lessen the influence of observation number 3. Okay.
Why is this the case versus point number 1?
Because of the location. This is in the middle of the x's. And all that's going to happen is just going to nudge it up. And you can actually, on your own, you can actually come up with a very, very small data set. And find points 1, 2, and 3 and actually see this happen. And where if you have observation 1 in the data set, or if you have observation 2 in the data set, or observation number 3, and you'll see, if you actually then graph them out, you'll see the same effect. I don't know, perhaps maybe I should have an example like that. I think I do. I might later. Yeah, I do it later on page 1024. But it's not too difficult to do this on your own, too. Now, the problem, obviously when we have simply one predictor variable, you can see what's going to happen. The problem is, what happens if you have 3 predictor variables, 4 predictor variables, 10 predictor variables? The same kinds of things can happen, but the problem is you can't necessarily graph it and see it happen as easily. So that's why we have some numerical tools available to us that allow us to evaluate particular observations to help determine when this happens. Okay. And these rely on looking at residuals. Obviously, a residual, E, is your response minus the predicted value. In Chapter 3, we looked at the semi-studentized residual, which basically put this on a nice scale for us so that we can say, if I have a semi-studentized residual outside of plus or minus 3, I have an outlier. Again, does not necessarily mean it's necessarily a bad outlier. It just means you have an outlier. But we're going to look at better measures. And there are going to be two better measures. And they all rely on the hat matrix. So you might remember in Chapter 5 and 6, I said we will come back to this hat matrix and play an important role in Chapter 10. Well, here's the role. Remember what the hat matrix looks like. It's x times x prime x inverse, x prime y. Essentially, if we call that h, if you take h times y, you put the hat on y. That's why it's called the hat matrix. Now, the hat matrix comes up in a number of places. In particular, in chapters 5 and 6, we looked at the covariance of E. E is a vector of all of our residuals. So it's measuring the variability and the association between residuals. And we showed it was sigma squared times the identity matrix minus H. The corresponding estimated covariance matrix, just take the sigma squared out and put an MSE in. So this is what the hat matrix looks like if I were to put it into a symbolic form. It's an n by n matrix, meaning every observation, we have n observations, and so that's where this n by n comes from. And so the diagonal elements here play an especially important role for us. Notice how I denote these diagonal elements. So row 1, column 1, H11. Row 2, column 2, H22, and so on. Then if we look at the covariance matrix of E, again, sigma squared times I minus H, if I put this all in the symbolic form, of course, the I is the identity matrix, so on the diagonal you have 1s, on the off diagonals you have 0s. Look what happens when you actually do the math there. the diagonal elements now become 1 minus, let's say, h sub I. The off-diagonal elements are negative h sub ij, let's say, row I, column j. And the reason why the diagonal elements are so important to us is this. If I were to find the covariance of E1 and E1, again, that just means the variance of E1. That variance is this, sigma squared times 1 minus H11. So now you have a measure of the variance of E1. The variance of E2 is sigma squared times 1 minus H22, and so on. Why is that important? Well, the whole purpose in the semi-studentized residual divided by square root of MSE was so that we get kind of like a standardized value. But I said, note that a standardized value, or some people call them studentized values, should have a variance of 1. By dividing only by the square root of MSE, which is the estimate of sigma squared, or square root of sigma squared, you don't end up actually getting a variance of 1. But instead, if I were to take E sub I times the square root of the estimate of sigma squared, now times 1 minus that HII value, now I get a standardized or studentized value. This has a variance of 1. In fact, it's going to end up having a t-distribution. We'll see more coming up. Before, I couldn't tell you exactly what that distribution was for that statistic. So the estimated variance of E sub I is MSE times 1 minus H sub I. And I put this together with my residual itself. I have what our book calls a studentized residual. Now, in your first stat course, you heard of the idea of a student's t-test statistic. It was often denoted as x bar minus mu over s divided by square root of n. Use that to do a hypothesis test for mu. Note that I could also write this as x bar minus mu times the square root the estimated variance of x bar. We are essentially doing the same thing here. So that's why our book calls this a studentized residual. You learned in your first stat course that this studentized value here had a t-distribution with n minus 1 degrees of freedom. The 1 was missing because you were estimating x bar. This quantity, the studentized residual denoted by r sub I, has a t-distribution as well with n minus p degrees of freedom. The p comes from the fact that you're estimating p different betas. So, given that this has a t-distribution, how could we detect outliers? With a t-distribution, you now know with a certain probability that all possible values should fall within about 2 different numbers. Let's say here, a quantile from a t-distribution here, quantile from a t-distribution there. So, how could you detect outliers?
That's the critical value of the t-distribution.
Well, yeah, these are basically critical values from a t-distribution. So in other words, look for these studentized residuals that are outside of these 2 values here. Because if I had let's say a value, let's say over here for a studentized residual, what that says is that that's quite unusual. You wouldn't normally expect that if all your model is working correctly. So because of that, you might be thinking, okay, well, maybe there's something wrong with my model because I have an outlier there. So that's how you can find outliers. Now, note that the mean of these R sub I values is not exactly equal to 0. It will be always close to 0, but not exactly. And it all comes down to the fact that we have that 1 minus h sub I in the denominator. You know, take a simple case where you have, let's say, a sample size of 3 and actually write out what R1, R2, R3 will be, and you'll see why things don't simplify exactly to having a mean of 0. Note that that's different from what we had with the semi-studentized residuals. And as I said earlier, we no longer will examine semi-studentized residuals. Okay. That takes us to page 10. So we have studentized residuals, and now we're going to have something called studentized deleted residuals that are also going to be very helpful to us. And this is related to something that we saw back in Chapter 9. Remember, in Chapter 9, we looked at something called the prediction error. Take your response variable for, let's say, the ith observation, subtract off its corresponding predicted value, where the model that was used to come up with this prediction did not include the ith data value in its calculation to come up with the model. So that's what that y hat sub I parentheses I stands for. That was the prediction error. Now our authors decided to call it a different name. Even though it's the same thing, they decided to call it a deleted residual. I think this name makes sense because basically you're deleting the observation from the data set, estimating the model, predict that observation that was deleted from the data set, and then get the residual, deleted residual. And does anyone remember why, looking at these things like deleted residuals are good to do? Okay. Let's see now. Put on test why deleted residuals. We want to look at them. Why they are good. You don't want to participate? That's what happens. Now, here's some background. Let's go back to a plot that we looked at a few minutes ago. If I remove observation 2 from my model, I'm sorry, let me start over. So we're going to look at E sub I, yi minus y hat I. We'll also look at D sub I, yi minus y hat I parentheses I. Suppose we just have this main, the observations of our data set are this main set right here. Okay? And let's say also I add observation 1. Do you think the residual and the deleted residual will be that much different? No. And if you remember why, because, again, what's going to happen to this model is just going to move up just a little bit. So essentially, the distance between observation 1 and the red line would be our deleted residual. The distance between observation 1 and the purple line will be the regular old residual. And we can see that there's not going to be much of a difference. So it doesn't really matter if you look at one or the other, you're going to get about the same answer. How about for observation 2? Will there be much of a difference? No, there won't be. Then with observation 3 then, again our model is going to look maybe something like this now. Will there be much of a difference between the residual and the deleted residual? Yes, there will be. That's why these deleted residuals are helpful. say, will pick up circumstances like this, where a regular old residual might not, let's say, pick it up as dramatic. I mean, this is kind of a dramatic example where I drew observation 3. But I think you get the point why the deleted residual is important. And that's why we want to look at it, in addition to just a regular old residual. Okay. So we have these deleted residuals, and what we like to be able to do is come up with a studentized value for them. So what that means then is that we have d sub I, and we want to be able to figure out, well, what do I divide d sub I by in order to get a studentized value, and then, as you will see, to come up with a t distribution for that particular value. So what we're looking for, what's this estimated variance? Well, we go back to something that we learned about in Chapter 2 and also then in Chapter 6. And that is, remember when we were doing prediction intervals? The estimated variance for a new y value and its corresponding predicted value, remember that this new y value basically is representing an observation that's not in our data set. That difference, we found what the estimated variance would be. It was MSE times 1 plus then a vector of your x values corresponding to this new observation, transpose it, take it times x prime x inverse, then times that vector of those x values again. We learned this back in Chapter 6. Essentially, we had the same circumstance occurring here with a deleted residual, because we're taking out that particular observation from the data set, estimate the model, and now predict it, that observation that was predicted, or the observation that was removed. We have essentially the same thing. So because of that then, to get a studentized value, then we divide by that variance. So notation here. This parentheses I basically is representing the MSE from the model that does not have the ith observation included in the calculations. Same thing then with this X matrix. Remove that ith observation from the data set, get your X matrix. What's the dimension of this X matrix going to be? What's the dimension of a normal X matrix? Yeah, this is going to be n minus 1 by p. So a normal X matrix would be, you have n observations, so you have n rows to your X matrix, and then you're estimating p different parameters, so that's the number of columns. So our authors, again, call this now a studentized deleted residual, and they denote these by t sub I. So how many different models are we going to need to estimate to calculate t sub I for every observation? N, because we have n observations. That could take a while. So it would be nice if we could come up with some way to do these calculations without actually having to estimate n different models, and fortunately we can. Note that it can be shown that a deleted residual is this. E sub I, your regular old residual, and just divide it by 1 minus h sub I. Don't worry about derivation, but that's a nice form for our deleted residual. So now we have a way then to deal with this numerator so that we don't have to estimate n different models. Also, the estimated variance of d sub I, which was in the denominator, can actually also be found to be then the MSE divided by 1 minus h sub I. So that's good. So what that leads us then to, if I were to put this component into d sub I, put this into the variance, this MSE, though, is still, with respect to removing the ith observation, I'm almost there. I almost have a statistic that I can calculate without having to estimate n different models. finally, on page 1012, one can show this nice little relationship between MSE and MSE sub I. Don't worry about it. So that if you solve for MSE I, then we finally get a statistic that can be estimated through just estimating one model. That's good. Okay. So now this T sub I has a T distribution with n minus p minus 1 degrees of freedom. Remember, a studentized residual had n minus p degrees of freedom. Why do I have n minus p minus 1? Because essentially one less observation. So that remove that one particular observation. So if I want to detect, let's say, outliers using this relationship, what do I look for? Extreme values, basically, with respect to this T distribution. So maybe find the 0.01, find the 0.99 quantiles from this T distribution. If I have anything outside of there, I have an outlier. Doesn't necessarily mean it's a detrimental outlier, it just means I have an outlier. Now, again, I guess actually corresponding to a discussion that we had earlier, notice what we're doing here essentially. For every single observation, you are doing this hypothesis test. HO, not an outlier. HA, uh-oh, you got an outlier. So if I have n different observations, I'm doing n different tests, that's a lot of tests. And you could have built up then a problem with your overall error rate, the family-wise error rate. So what can you do? Well, our authors recommend using a Bonferroni adjusted critical value. We've talked about the Bonferroni procedure before. And they say simply this. Instead of just having alpha divided by 2, put alpha divided by 2 times n there. So that 2 times n is in the denominator. Alpha then divided by 2n. You can do this with the studentized deleted residuals and also a similar thing with the studentized residuals. So if I have something that falls outside of there, then you start worrying about that observation. It's an outlier, but again, you don't know necessarily if it's detrimental or not. No, more so with the studentized deleted residuals. It's more clear than it would be. Now, there's a problem here, though, and that is, suppose you have a large sample size. What's going to happen to these critical values? Excuse me? They're going to, let's say, increase in absolute value. So, you can say the window here, if you want to call this a window, since you're between two different numbers, that window is going to be bigger, 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 and the more observations you have, so the less ability that you will have to detect outliers. So here's my general recommendations of what to do. Well, use our book's Bonferroni procedure, but also at least take a look at some of these non-adjusted critical values as well. And if you see something outside those non-adjusted critical values, you might start to suspect maybe there might be some issues, some outliers. Okay. Here's another question. Suppose indeed everything is actually okay with your model. Your model is great, but you do have you end up having some of these studentized residuals and studentized deleted residuals, a few, outside of those range. Is that necessarily surprising? No? Why not? Yeah. Let's say if I have a sample size of 100 and alpha is 0.05. I would generally expect about 5 to be outside that range. So when do I start getting worried? Well, when I'm, let's say, a lot more than 5, or if, let's say, I have some observations that have, let's say, a T sub I that might be, let's say, 5 or 10, something that's very large. then that's when I work. But if you have some that are just a little bit outside, and there maybe if you're using alpha 0.05, and there's about 5 of them, and then that's okay. That should be expected. And also something I think I forgot to mention out loud here in my advice section here. When I do this number 2, I usually take a low alpha, 0.01. I think that's helpful so that you're not, let's say, being too alarmist in finding issues with your model. Why don't we go ahead and stop there? And we'll pick up next time, and because I don't think we'll get through the whole example. And we'll pick up next time talking about these residuals. Are there any questions? Okay, that's it for today.